Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 4 on data distribution shapes. So far we have seen a lot of different statistics throughout this unit and in previous courses. Now, which statistics that we use to answer our statistical questions just might depend on how the data distribution is shaped. It's a little bit weird, but let's kind of get into it. Now, the shape of a data distribution. When we look at the values of a data set on a dot plot, a histogram, or a box plot, we're looking at how the data distribution is shaped across the range of the data, okay? And that is very, very important because if it looks one way or another, that will affect which types of statistics we should or we can use in order to answer our statistical question. So let's take a look at exercise number 1. Two data distributions are shown below that each contain 500 data points. All right, so you got data distribution A in blue, data distribution B in red, although on your worksheets they're just in white and black. All right, letter A. Although neither are perfectly symmetric, which of the two data distributions is more symmetric? Explain your choice. All right, well, you have certainly seen the words symmetric and symmetry before, not just in this class, but in other classes. So pause the video now and tell me whether data distribution A or B is more symmetric, and then tell me why. All right, well, symmetry all sort of means it looks the same on one side of a vertical line as it does on the other side of a vertical line. And for that, data distribution A is certainly more symmetric, right? It looks basically the same whether you're going this way or whether you're going this way, right? Whereas data distribution B looks very different if you're going to the right than if you're going to the left. So my answer to letter A is choice A, because the left and right look roughly the same, right? I could fold it over some kind of vertical line and it would, roughly fall on itself. Now, let's take a look then at letter B. What is true about the mean and the median of the more symmetric distribution, right? So take a look at the mean and the median of distribution A, and what can you say about those two values? Well, one of them is 29.1, one of them is 28.9. Those are very close to being the same. Now, I think it actually kind of helps to contrast that with data distribution B, right, where we have a mean of 30.1 and a median of 28.9. Now, you might say, well, those are pretty close to being the same. These two are different by 0.2, by 0.2, right? These two are different by 1 2/10. That's a lot more, in terms of the grander scheme of things, okay? So in a symmetric distribution, the mean and the median will always be roughly the same. In a perfectly symmetric distribution, they will be exactly the same, all right? But in a pretty symmetric distribution, they will be roughly the same. Now let's take a look at letter C. What effect does the right skew of the asymmetric distribution have on its mean? All right, well, before we kind of get into any of that, let's talk about the terms that are bold-faced there. First, the right skew, okay? What a skew means is that basically there's a tail that points off in one direction. So here we've really got this thing kind of extending in this direction and extending in that direction. But in this particular distribution, the distribution kind of stops here and extends way out to the right. That's what's called a rightward skew or a right skew. Now, the fact that the distribution is not symmetric means that it is asymmetric. All right, so back to the question. What effect does the right skew of the asymmetric distribution have on the mean? Well, the mean of this is 30.1 and the median is 28.9. What it does is, because there are these larger values that push way out here, it makes the mean significantly larger than the median, or it causes the mean to be significantly greater than the median. Now again, you might say significantly greater, it's only 1.2 units greater, but that could make a huge difference in terms of our analysis and the way that we're thinking about central tendency and things like that. Now, if it was a leftward skew, if the tail had extended out this way instead of extending out that way, it would have caused the mean to be less than the median, right? The median is just the middle number. It's somewhere like right in the middle. But when you've got this, like, these very large values that are kind of skewing one way or the other way, but not both ways, then it pulls the mean in the direction of the skew. Let's take a look at letter D. How can you describe the variation within the two data sets? All right, well, this is kind of interesting. Think about this a little bit and look at the measures of variation that we've been given. All right, well, if we look at the IQRs, the IQR here, which is a measure of variation, is 10.7, and here it's 10.6. So the middle 50% of the data has roughly the same variation. Let's write that down first. Based on the IQR, the middle 50% has roughly, keep using that term, the same variation. But look at the other measurement of variation we have. In the symmetric distribution, the standard deviation is 7.5. Very small on the screen, I apologize for that. And in the asymmetric distribution, the standard deviation is 9.2. That's significantly higher, significantly higher. And again, it's all about those kind of skewed values out here causing the average distance that a data point is away from the mean to be much larger. So I'm going to write that down as well. But the standard deviation of data set 2 is much larger. Again, you might say much larger, 9.2 versus 7.5, but that is considerably larger, right? The average, distance that a data point here is away from the mean is 7.5, but here it's 9.2. And again, that's a little weird because the variation in that middle 50% is like, that's almost identical, 10.7, 10.6. But the standard deviation of this one is much higher because of that skew. Okay, now this is all getting to a very, very important thing. Very often when we discuss statistics for a data set, we need to pay attention to whether the data is symmetric or whether it is skewed to the right or left. Exercise 2, fill in the following. A, use the mean and standard deviation to represent a data set when the data distribution is symmetric. All right? So, statisticians would always prefer to use the mean and the standard deviation. They're the gold standard of the central tendency and of the variation. But what we saw in the last exercise is that if a data distribution is skewed, then the mean, right, that gets too far away from the median, and the standard deviation tends to be a little bit too large, right? On the other hand, letter B, when the data distribution is skewed, then the blank and the blank should be used. So keep in mind, right, in that last exercise, right, whether or not it was skewed or wasn't skewed, the medians were basically the same and the IQRs were basically the same. So when you have a data distribution that's skewed or has outliers or anything really funny going on, it's not typical whatsoever, then we should use the median and the IQR. All right? The median and the IQR are not tend to be thrown by skew or outliers because they're just the middle number and the middle 50%. They don't really care what's going on in the fringes, right? On the other hand, the mean and the standard deviation both kind of get heavily influenced by any kind of skew in the distribution or any kind of outliers. Speaking of outliers, let's take a look at the next exercise. Sometimes there can be data values that lie far away from the rest of the data set, and these are known as outliers. Outliers can cause issues similar to what we saw with skewed distributions. And you can kind of almost think about this as being like a distribution that is skewed off to the right. Now there's a technical definition for what an outlier is, and we're not going to get into that in this course. You'll take a look at that a little bit more in Algebra 2. We're going to be like just informally assessing outliers, i.e., that's an outlier. Okay, but let's take a look at exercise number 3. Lucas harvests 15 tomatoes from his garden and finds their weights in ounces shown below. All right, so Lucas has got, 15 tomatoes. Most of their weights are down there in that, in this kind of area. And then there was this one monstrous tomato that he pulled off. Okay? Letter A. Use your calculator to find all of the following measures. Round any non-whole numbers to the nearest tenth. All right, so this is another one of those issues where I've got to take the data set and I've got to, transcribe it from a dot plot into a list on my calculator. And that's a bit of a pain, and as we've talked about in previous lessons, how you enter data in your calculator is very calculator dependent. So what I'd like you to do is pause the video now and enter this data. Keep in mind, you're going to be entering 116, 117, but 3 18s, 119, 2 20s, no 21, 2 22s, 2 23s, 24, 26, and I guess that's a 44. So pause the video now and get those all into your graphing calculator list. All right, well, let me open up my calculator now. All right, I can actually just go in and open it. I've already put it into my calculator previously. All right, there we are. The weights of my tomatoes starting with 16 and going up to 44. All right. Now again, how you actually do statistics is very calculator dependent. On the TI Inspire, once I've got my data in my list, all I have to do, let me move this a little bit over here so I'm not breaking my back, is I just hit Menu, I go to Statistics, Statistical Calculations, I want one variable statistics, I've got one list, that's all good, I'm going to hit Enter, and there's all of my data. And I can get a variety of different things. I'm going to have my mean here, right? My mean is 22. Oh, that's nice. My standard deviation is 6.7 rounded to the nearest tenth. And we'll get all of that other stuff in just a moment, right? What I need to do is, in order to write it all down, I need to put it on my handheld only. Okay, so I can go into my, whoops, that didn't work. Let's try that again. Keep it always in front. It disappeared. All right, now let's move this thing up. My mean is 22. Let me just kind of move on down. My standard deviation is 6.7. That's going to go right in there. I'm looking for my median and my quartiles, etc. Here we go. My median is 20. My first quartile is 18. My third quartile, back and forth, is 23. And we'll calculate our IQR in just a moment. All right, let me put this back on full screen, right? Again, all of the data on the TI Inspire, or all the statistics once you've run the program, are going to be sitting here. You just have to sort of like go up and down to find them. It even has my max and the min. You just can't have a runaway calculator. Yours probably won't. Let me put this away for right now. All right, the IQR, right, the interquartile range, can be calculated by doing the third quartile minus the first quartile. So that's going to be 23 minus 18 for an IQR of 5. Awesome. Okay. Simple enough, right? We've all got all of our statistics. Now, letter B, we've already kind of gone there. Which value is an outlier in this distribution, right? That's pretty obvious, right? An outlier is basically a data value that is far away from the vast majority of the other data with a large gap between it and that data. And so it's pretty obvious that an outlier is 44. Right? So, letter C, what effect does it have, i.e. the outlier, does it have on both the mean and the standard deviation? All right, well, we just talked about it. Because that outlier is an outlier going out to the right, it's going to make both the mean and the standard deviation much larger. It will make both much larger. Right? It will make the mean larger because simply, right, how you calculate the mean is you add up all the values and divide by how many there are. So if there's one value that's really huge, right, then suddenly when you add that into all the other ones and then divide by how many there are, it's going to make it more larger. And you can already see, right, the mean is 22, but the median's only 20. Remember from our last exercise, if you've got this beautifully normal, well-behaved population or sample, the mean and the median will be roughly the same number. As well, right, the standard deviation is the average distance that a data point is away from the mean. And given that that 44 is, 22 units away from this mean, it really makes that standard deviation much larger. All right, let's take a look at letter D. Draw a box plot below the number line for this data set. All right, so this is kind of nice. I love to see these where we have a dot plot, right, maybe above the number line, and then we have a box plot below the number line, right? We can visualize how the data is distributed in two different ways in that sense. So what I'd like you to do is pause the video now and draw a box plot down here for that data distribution. All right, well, remember how we draw a box plot, right? We put a line at the minimum. We put a line at the maximum. That's pretty easy. We put a little vertical line at the first quartile. That's at 18. We put a line at the median. That's at 20. And we put a line at the third quartile, which is at 23. We put a box right around that 50% of the middle data. And then we extend whiskers out to the maximum and the minimum values. And this is a real telltale sign of an outlier, a really long whisker that is extended from the box either to the right or to the left, right? That indicates that, there is a huge distance between the third quartile and the maximum, and in theory, there really shouldn't be. All right, so letter E. Construct an interval for values that are within one standard deviation of the mean. All right, we've done this quite a bit, so I'd like you to construct the one standard deviation interval about the mean for this particular sample. All right, well, all we have to do is take the mean and subtract one standard deviation, and take the mean and add one standard deviation. So if we recall, our mean is 22, our standard deviation is 6.7. So we're going to have 22 minus 6.7 and 22 plus 6.7. That's going to be 28.7. That's going to be 16 minus 0.7. So that's going to be 15.3. Right. So any value between 15.3 and 28.7 will lie within one standard deviation of the mean. Now, one question we've asked time and time again once we have this interval is letter F. Let's take a look. How many of the values in the data set fall within one standard deviation of the mean? All right, so how many of those data points above, and we'll go back to that plot in a moment, fall in this interval? Pause the video now and go ahead and do that. I would even suggest circling all the ones that are within it with one large circle, not like a bunch of small ones. Pause the video and go ahead and do that. Now think about it. This is going to be anything from 16 to 28, right? The first one we can circle is 16. The last one we can circle is 28. 16 to 28. Well, geez, I mean, our smallest one is 16, and 28 is right here. So literally, all of these fall within one standard deviation of the mean. All right, I think, what did we say? Did we have 15 overall? 15. So 14 out of the 15 fall within one standard deviation of the mean. Okay, now letter G. Why is the answer to F unusual? Pause the video now and think about this a bit. Well, let's figure out what percent this represents. It's going to be a little bit messy, but let's do 14 divided by 15 times 100. Let's figure out that percent real fast. 14 divided by 15. Whoops, that doesn't help. 14 divided by 15, that's what happens when I'm just going way too fast, right? So that didn't work. Again, going too fast. So 93% roughly. I'm going to say this is about 93%. So why is that unusual? 93% of the data falls within one standard deviation of the mean. Well, in our last lesson, what we talked about was that in typical well-behaved populations and samples, about 67% of the data should fall within one standard deviation of the mean. This is closer to 2 standard deviations of the mean. That was 95%. So this is unusual because only about 67% should fall within one standard deviation. All right, and that really illustrates what's problematic about the outlier, right? The outlier is making the mean larger, which in and of itself isn't too bad in here, but because it makes the standard deviation so much larger, right, that interval that contains one standard deviation of all the values, right, that are within one standard deviation of the mean is far too large, right? One standard deviation of the mean is supposed to be including just the typical values, but this is including basically everything, right? Everything. So let's take a look at letter H. When specifying typical values within this data set, would it be better to use the interquartile range or the one standard deviation interval? Explain. Okay, well, pause the video now and write down your answer. All right, well, we should be using the IQR, right? And it's really simple. It's really what I was just talking about. If we use the one standard deviation interval, the problem with that is that's no longer the typical values, that's basically everything, right? That's basically all of the values, and that's happening because of that outlier. On the other hand, the IQR isn't being affected by that outlier one bit. We could move that outlier way back so that it was almost at the data set itself, and the IQR wouldn't change a bit. So we should use the IQR because the one standard deviation interval is giving us too many values. And again, this just goes back to what we talked about in that first exercise, which is that if a distribution has a skew in one direction or an outlier in one direction, it is much better to use the median and the IQR to represent the data set than the mean and the standard deviation. On the other hand, if you've got a beautifully symmetric distribution, right, then it makes all the sense in the world to use the mean and the one standard deviation interval to represent typical values within the data set. All right, let's wrap this up. So whenever we're trying to answer a statistical question, whatever that question is, how tall is a typical 9th grade student, or, how much money does a typical phone app developer make, et cetera, we almost always want to report some value of central tendency, either a mean or a median, and then we typically want to, represent some kind of range of typical values, either the IQR or the one standard deviation interval. The problem is, which ones we use really depend on the shape of the data distribution. If the data distribution is nice and symmetric, then the mean and the standard deviation are almost always the choice that you should go with. On the other hand, if you have either a skew going on in the data distribution or an outlier, you should consider using, and really should use, both the median and the IQR. All right, we're going to see this a little bit more in our next lesson when we compare samples from two different populations. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.